So combinations and permutations, what's the difference? Okay. In English, we use the word combination loosely without thinking if the order of things is important. In other words, my fruit salad is a combination of apples, grapes, and bananas. We don't care what order the fruits are in. They could also be bananas, apples, and grapes, or grapes, apples, and bananas. It's the same fruit salad, okay, right? Or the combination to the safe is 472. Now, do we care about the order? Okay. Could 724 work? No. Okay. So the order there is important. The order I put my fruit into my fruit salad doesn't matter because it's all going to get mixed together anyways. But with a combination lock, the order matters. So in mathematics, we use more precise language. If the order matters, it's a combination. If the order does not matter, it's a permutation. Okay? So there's the first two definitions you're going to need. All right, so really, this should be called a permutation lock and not a combination lock, because a permutation order matters, because 472 is the only thing that works. If I do 274, it's definitely not going to work. So a permutation is what we would call an ordered combination. So to help you remember it, think permutation and position. So permutations with repetition. Okay, these are the easiest to calculate. All right. When we have n things to choose from, we have n choices each time. So when choosing r of them, the permutations are n times n times n times n r times. Okay. So for instance, okay, well, let's go here. In other words, there are n possibilities for the first choice, then there are n possibilities for the second choice, and so on, multiplying each time. So for instance, if we had a deck of cards, all right, we shuffle the deck of cards, we pull a card out. Okay, the possibility of getting a specific card is a certain number, right? Okay, 1 out of 52. Okay, there's 52 choices for the first card. If I put the card back in, I shuffle them again, I still have 52 cards. And so for my second card, I have 52 choices for that card. Okay, and do it again, I still have 52 choices for each card. Okay, which is easier to write as an exponent? So we could say, instead of n times n times n r times, we could say n to the r power. Okay. So in the example above, in the lock, there are 10 numbers to choose from. 0 through 9, okay, the digits. Right? Now, when people think of digits, they think of 1 through 9, but you got to remember, 0 is there also. So there's 10 different digits when we're talking about numbers. Okay? And we're going to choose 3 of them. So that combination lock that we are working with up here, right, since there are 10 choices for the first one, and 10 choices for the second one, and 10 choices for the third one, then there are actually 10 to the third power choices, or 1,000 different permutations. Right? So that bike lock you've got that has 3 different digits on it to choose from, there's 1,000 different possibilities there. Okay? Permutations. Okay? Not combinations, but permutations. Okay? So this formula would be n raised to the r power, where n is the number of things to choose from, and we are choosing r of them. In this case, repetition is allowed. So when we actually talk about permutations and combinations in a more in the fashion that we're going to look at in a minute, okay, order is not going to, or repetition is not going to be allowed. But right now in this situation, repetition is allowed and order does matter. Okay, when we're using the formula n raised to the power of r. And this is similar to the first 2 questions I asked you here. Okay. How many different ways can you select the top and the bottom? How many different sundaes could you make? So we call this, we have the fundamental counting principle is what you used for those. And the fundamental counting principle basically says that however many things I have, I'm going to multiply them together. So with our example back here of our tops and bottoms. We had 3 tops and 4 bottoms. So 3 times 4 is 12. So if you made a tree diagram to draw that out, okay, you had 3 choices for the first thing, 4 choices for the second thing, and we just multiply them together. Okay? So that's the fundamental accounting principle works that way. When it came to the sundaes, okay, we had 3 choices for our ice cream, 2 choices for our flavor we put on top of the ice cream, and 3 different choices for nuts that went on top of that. So we had 3 times 2 is 6, times 3 is 18. Those things all belong to the fundamental counting principle. So here we're going to make a yogurt parfait. We have a yogurt flavor, we have fruit, and we have nuts that are going to go on top of this yogurt parfait. And so using the fundamental counting principle, we're going to take those options and we're going to multiply them together. So we have 2 options for our flavor and 5 options for our fruit and 3 options for the nuts. And then we're just going to multiply them together. So there are 30 ways to make this yogurt parfait. Two times 5 times 3. And that just uses the fundamental accounting principle. Okay, I have 2 choices for the first thing, 5 choices for the second thing, 3 choices for the third thing, and so I'm just going to multiply them together. Most of what we do in this chapter is going to be completely with multiplication. Right? We will rarely do any adding. Password. How many of you have passwords? Okay, all right. We all do. All right. We've got Twitter. We've got Facebook. We've got Instagram. We might have Pinterest and Vine now too. Right. All right. Anything else? Okay. Google. Okay. Your school login and password. So you've got lots of different passwords. All right. So what we're going to look at is how can I figure out how many different ways there are to create a password? Okay. Well, it depends on how many characters you use, right? We can use digits, and we can use words or letters, and we can use special characters like the @ sign or a $sign or both. Okay. Well, this password in this case consists of 4 digits followed by 2 letters. The letters A and Z are not used. And each digit or letter may be used more than once. Okay? Well, since it says more than once, that means we have repetition. So this is similar to what we were just talking about with the permutations here, n raised to the power of r, is that we have repetition is allowed in these cases. Right? So you want to know how many unique passwords are there? Well, how many different characters are we using? How many characters are there for this password? Total. There are 4 digits and 2 letters, right? So to help me out with this, I'm going to make 6 dashes here, okay? To represent the 6 different characters in my password. Or it could be a combination lock with 6 different digits or many different things. So the password consists of 4 digits, first of all. How many digits are there? There are 10, 0 through 9. Okay? So for the first digit in my password, I have 10 choices. Okay? I have the numbers 0, 1, 2, all the way down to 9. Okay. Can the next digit in my password be the same as this digit here? Yes. Okay, so how many choices do I have? I have 10 again. Okay. The third character in my password is also a digit. How many choices do I have for that one? I have 10 again. Okay. And the fourth character in my password is also a digit, so I have 10 choices there. Well, then it says it's followed by 2 letters. But A and Z are not used. Well, if A and Z aren't used, how many letters do I now have? 24. Okay, so I have 24 choices for the first one. Can I reuse that letter? Yep, so then I have 24 choices for the second one. So to find out how many different possibilities there are with passwords, then I'm going to multiply these together. So 10 to the 4th power times 24 squared. Right? Or is it 576? It's what? 576, okay. Okay, so there are 5,760,000 different passwords with 4 digits and then 2 letters. So, if somebody's trying to steal your password, it takes a lot of work. It really does. Even though it happens sometimes, right? But it does take a lot of work. Okay. So, right, this is the fundamental accounting principle. Also uses this permutations we talked about here then, right? Where repetition is allowed and order matters. Okay. All right, so now we're going to look at permutations without repetition. Okay. So in this case, we have to reduce the number of available choices each time because we can't have the same thing over and over again when repetition is not allowed. For example, what order could 16 pool balls be in? So if I put the 16 pool balls in order, okay, how many choices do I have for the first one? 16. How many choices do I have for the second one? 15. And then 14, and then 13, and so on. All right? So I could order them, and I would get a lot of different possibilities. Okay? All right, so you can make that your password. 16, 15, 14, 13, 12, 11, 10. All right, that would be a long password. Right? But for somebody to be able to break that password, they'd have to go through 20 trillion different possibilities to get yours. Well, maybe we don't want to choose them all. Maybe we just want to choose 3 of them. Well, so that means we have 16 choices for the first ball, then 15 choices for the second one, and then 14 for the third one. So there's 3,360 different ways I could order 3 balls from 16. So without repetition, our choices get reduced each time. But how do we write that mathematically? We can use what's called a factorial function. So the exclamation point is used for the factorial function. All right, and I'm going to tell you where it is so you can find it. So if you go to math and then to probability, PRB, you'll see, I think it's number 4 is the factorial symbol, right? Okay. So when we were doing those warm-ups, of 5, 4, 3, 2, 1, that's what 5 factorial is. And when you see that factorial symbol next to a number, that means I'm starting with that number and multiplying all the numbers less than that, okay, by it until we get down to 1. So 4 factorial is 4 times 3 times 2 times 1. Okay, there's our 24. 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, 5,040. Okay. Note, it is generally agreed that 0 factorial is 1. It may seem funny that multiplying no numbers together gets us 1, but it helps to simplify a lot of equations. Okay, so if 0 factorial comes along, then that is equal to 1. Just like anything raised to the power of 0, we say that that is equal to 1 also. Okay. So, but when we want to select, if we want to select all 16 billiard balls, right, we would say 16 factorial. But when we want to just select 3 of them, we don't want to multiply after 14, but so how do we do that? There's a neat trick. Okay? And the neat trick is then we're going to divide by 13 factorial. So if we had 16 factorial divided by 13 factorial, okay, that would simplify it down. So really all we're multiplying is 16, 15, and 14. Now here's my thing I'm going to tell you. Okay? It's way easier just to do 16 times 15 times 14 than to say, okay, I've got to do 16 factorial divided by 13 factorial. Okay? But the reason we talk about the whole thing is because when we get to combinations, okay, it adds a little bit to that we need that whole thing. So here's a formula for finding permutations when there's no repetition and order matters. So this is the formula for permutations, that you have n factorial in the numerator and n minus r factorial in the denominator, where r is the number of things we're choosing. N is how many things we have, and r is how many things we're choosing. All right, so in this case here, we had 16 pool balls, and we're choosing 3 of them. Now there's a couple different ways you will see that written. Okay? And it can be written as a couple, specifically down here. So permutations can be written a couple different ways. You could see permutation of n choose r. It could be like this middle one here, NPR. But the one that we will use and see the most is going to be this one here. This is what we'll use. Okay? We have a permutation of n items, and we're choosing r of them. Okay? And then that gives us this formula here for permutations. All right, and they give us another example here. Say, okay, how many ways can first and second place be awarded to 10 people? Well, I have first place and second place. Here's where I like to use those little line segments. Okay? How many choices do I have for first place? Well, there's 10 people, so I have 10 choices for first place. How many choices do I have for second place then? Well, if one person got first place, then there's only 9 left to get second place, right? Because there's no repetition. The same person cannot get first and second place. Right? The 8 ball can't be in the first and the 9th spot when I order the balls. Okay? So there's no repetition. Right? So permutations, n. So I have a permutation of n choose r, and it gives me that formula there. But basically all that means is I'm going to take, okay. So I start with 10, I'm choosing 2, so I have 10 and 9. Start with 16, choosing 3, 16 times 15 times 14. All right. So this is kind of like our A, B, and C we did in our warm-up. There are 3 choices for the first letter, 2 choices for the second letter, 1 choice for the third letter. Okay. 3 times 2 times 1. Okay, here we have, they wanted to find out how many ways can a student government select a president, vice president, secretary, and treasurer from a group of 6 people. So the thing you have to ask yourself, first of all, is does order matter in this case? Right? And back in that first discussion about permutations and combinations, we said permutation and position go together. Right? Do these specifically have a position? And the answer is yes, because we have in order a president, and then we have a vice president, and then we have a secretary, and then we have a treasurer. Okay? Order matters here, because somebody is getting those specific positions. First and second place in a race. Okay? Those are specific positions, so that would be a permutation. Right? So order matters. Can somebody be more than one? No. Okay? So we have order matters and no repetition. I'm spelling that wrong, aren't I? There's R-E-P-E, isn't it? Okay, order matters, no repetition. Right? So how many choices do I have for the president? Okay, there's 6 people, I have 6 choices. How many choices do I have for the vice president? 5. Secretary and treasurer. Okay? So all I need to do is multiply them together. Now if we want to write it out using our formula, okay, this is a permutation of 6 people, and I'm choosing 4. So we would have 6 factorial in the numerator and 6 minus 4 factorial in the denominator. So it would be 6 factorial divided by 2 factorial. Which either way you do this, all right, you're going to get 360 different ways. Bless you. So either way, there are 360 ways to get to different 4 people. Okay. All right, so you do this one. All right, so 6,720 different ways we could arrange 5 of 8 vases. So you have to remember that the bigger number is that's how many options I have, and the smaller number is how many I'm going to fill. Okay, I'm going to fill those positions. So once again, this is order matters because I'm lining them up from left to right, and repetition is not allowed. Okay. So combinations, true combinations. Okay. There are also 2 types of combinations. One where repetition is allowed, such as the number of coins in your pocket, or no repetition, such as lottery numbers. Combinations with repetition, these are the hardest to explain, so later. Okay, we're not actually going to spend time with them in this class. Combinations without repetition, this is how lotteries work. The numbers are drawn one at a time. If we have the lucky numbers, no matter what order, we win. The easiest way to explain it is assume that order does matter, which is permutations, and then alter it so that the order does not matter. So basically what we're going to have is we're going to have permutations divided by the order of those things that we have. Okay? So going back to our pool ball example, let's say we just want to know which 3 pool balls are chosen, not in order. So we already know that 3 out of 16 gave us 3,360 permutations. But many of those are the same to us now, because we don't care what order they're in. So maybe I have the 16, the 15, and the 14, or the 15, the 16, and the 14. I don't care. All I'm concerned with is I got 3 pool balls. For example, let's say balls 1, 2, and 3 are chosen. These are the possibilities. So we could have these 6 permutations of the numbers 1, 2, and 3, but when it comes to combinations, when order doesn't matter, it only represents 1. Okay. So in this situation, then, I would have to divide the number of permutations, 3,360, by 6, because there are 6 different permutations I can do with the numbers 1, 2, and 3. So in fact, there's an easy way to work out how many ways 1, 2, and 3 can be placed in order. We've already talked about it. Okay, there are 6 ways. If there's 4 things to be placed in order, then there's 24 different ways. So we adjust our permutations formula to reduce it by how many ways the objects can be placed in order. So when we have combinations, then, right, here is the formula for combinations. It's n factorial divided by r factorial times n minus r factorial. So basically what we're doing is we're just dividing the permutation by the number of ways those things can be selected. And for a combination, we will write it as a combination of n choose r. Where once again, n is the number of things to choose from, and r is how many we are choosing. And this is also known as a binomial coefficient, because remember when we were expanding things in chapter 6, we said x plus 3 to the 5th power. Right? All of those coefficients are actually combinations for all of them. Okay. So our pool ball example now looks like this. 16 factorial divided by 3 factorial times 16 minus 3 factorial. Or 16 factorial over 3 factorial times 13 factorial. So basically what we're doing is taking a permutation and dividing it by how many ways those things can be put in order. 3,360 divided by 6. So remember, do the permutation, then reduce it by a further r factorial. Or remember the formula. All right. So, combinations. Order does not matter. There are 12 different colored cubes in the bag. How many ways can Randall draw a set of 4 cubes from the bag? There are 16 cubes in the bag. How many ways can Randall draw a set of 4 cubes from the bag? So first we have to decide, does order matter? Is he putting those 4 cubes in an order? Okay. And the answer is no. So order does not matter. And there's no repetition. So this is a combination. So we're going to do a combination of 12 items, and we're going to choose 4 of them. So here is really where your fraction key in your calculator comes in handy to do this easiest way. Because this would be 12 factorial in the numerator. And then in the denominator, we have 4 factorial and 12 minus 4 factorial. Okay. So the thing about combinations is these 2 numbers in the denominator have to add up to the number in the numerator. Okay. 12 factorial divided by 4 factorial times 8 factorial. Or if you want to do the permutations, okay, think of it as a permutation divided by the order, then we would have 12 times 11 times 10 times 9. There's our 4, divided by 4 times 3 times 2 times 1. Okay. Because there's this, the numerator is how many permutations there are. In the denominator way is how many of those ways can be ordered. So you can think of it as either way to do this problem. And you get 495 different ways he can choose 4 cubes from a bag of 12. Thing to remember, all right, we have the fundamental counting principle, multiply things together. Permutations, order does not matter, or order does matter, no repetition. Combinations, order does not matter, and no repetition. And you can use those formulas then to be able to find those.